Let's take a look at this problem here. We have a source-free RLC circuit. So let's go ahead. So we have a source-free RLC circuit. And just like with any other problem, you want to recognize the type of circuit you have so that you can approach it with regards to solving it properly. So this is the typical source-free, and what I forgot to mention was it's a series, source-free series RLC circuit. So you got the RLC in series, and you're given the value for R, you're given the value for the inductance, and we're asking what value of C will make this series circuit overdamped, critically damped, or underdamped. Okay, so to do that, we want to go back and look at the definitions of what overdamped, critically damped, and underdamped is. So if we go back to the definitions, that's going to look at the relationship between alpha and omega naught. So for overdamped, alpha has to be greater than omega naught. For critically damped, alpha has to equal omega naught. And for underdamped, alpha has to be less than omega naught. Okay, so to approach this, so we have to back up and say, well, what is alpha and omega? Again, we defined this previously, where alpha was equal to 1r over 2l, and omega naught was equal to 1 over the square root of LC. Okay, the nice thing here is we're given the values for R and L, and we just need to figure out what the value of C to determine what would make it in those ranges. Now remember, when we did the definition of these different states, we also said, well, for all of these, when we compared alpha and omega, we said the definition was, we looked at C as it related to 4L over R squared. And this is where we said, well, this could be greater than, this could be equal to, this could be less than. Okay, we didn't derive it, but just for the sake of derivation here, we can say that our alpha is our R over 2L. Let's just say it's equal to our omega naught, which is 1 over the square root of LC. We can square both sides. If we square both sides here, we get R squared over 4L squared equals 1 over LC. Rearrange, we get R squared equals 4L squared over LC. All right, and then that will eliminate the L from here and one of the L's from there, and then we can rewrite this equation. We'll come up here, and we got R squared is equal to 4L over C, and then just rearranging for C equals 4L over R squared. And that's where we're getting that relationship from. So I just used the equal to derive it, but essentially by changing the equal to sign to greater than or less than will give us that relationship. Okay, so that's where this guy comes from. Okay, so just to back up and just clarify that. All right, so it's as simple as that. It's as simple as plugging in those values. So if we say C is greater than, for the first part, 4L over R squared, well, we know that our L is 1.5 henries, our R is 50 ohms. We square that. Okay, and then we get, that's 2500 in the denominator, 2.4 times 10 to the minus 3, or we can just say that is 2.4 millifarads. Okay, so that's going to be our key number here, 2.4 millifarads. So for the overdamped, your C has to be greater than that. For the critically damped, C has to be equal to that. And for underdamped, C has to be less than that. So that's essentially what you're doing for this problem. So let's just go ahead and write that down. So scroll up just a little bit. So for overdamped, C has to be greater than 2.4 millifarads. For the second part, critically damped, C has to equal 2.4 millifarads. And then for the third part, underdamped, C has to be less than 2.4 millifarads. Okay, and that's essentially the three different stages here, and it really depends on your values of R and L to determine what the rest of them will be. And then you can rearrange it some more if something is given and another isn't. But essentially that's all you need to do for this problem. Okay, we'll do another problem related to source-free series RLC in the next video.